This is a lesson on early atomic models. The first group that thought of things of atoms were the Greeks. The ancient Greeks came up with the idea that there are 4 elements: earth, air, fire, water. So there are 4 elements. Of these Greeks, most of them thought matter was continuous. Aristotle, for one, but there were a very small minority called the atomists who believed that matter consisted of very, very small chunks differentiated on a geometric scale. They look different because they're different geometries. Greeks loved geometry. In the Middle Ages, alchemists came around and they did a lot of experiments. They came up with many of the lab equipment and many of the lab procedures that we have today. They were hands-on because they were trying to make things, elixir of life or gold, base metals into gold. The Greeks, on the other hand, were all theorists. They didn't want to touch their hands. So the alchemists and the Greeks were opposite of each other. Modern Boyle systematically, and this is the starting in of the difference between ancient science or mysticism to modern science, systematically studied volume versus pressure, and he came up with Boyle's law. So he started up doing a scientific method. He came up with the background, the first indication that scientific methods based on multiple trials, systems, and variables, and measurements. Lots of measurements and systematic study. Modern chemistry starts with the disapproval of phlogiston. Phlogiston was the last of the elements. This is the element of fire, renamed, and this is the oxidation. They kind of thought phlogiston was oxygen, sort of, kind of. So when they studied that, there's an English chemist called Priestley and the French scientist called Lavoisier, who both did steps on this. Lavoisier came up with the law of conservation of matter, or mass. Sometimes they call it mass, sometimes they call it matter. And he's the one that did the experimental background that led up to the idea that phlogiston does not exist. Proust, German, he came up with law of definite proportions. That means that if you have more than one compound made up of the same elements, this says if you have a compound, it has a set called percent or ratio of elements. If you have a compound that's 13% oxygen, then no matter where you find it, that compound is going to be 13% oxygen. If it's 73% oxygen, then it's not that same compound. So this is a set percentage of elements or set ratios of elements, so that's a definite proportions. Dalton came up with the first modern atomic theory. He combined ideas of Lavoisier, Proust with the atomists, and came up with a set of rules for the modern atomic theory, which we'll get to in a little bit. And he came up using that, a law of multiple proportions. Well, let's do the atomic theory first. The atomic theory all matter is made up of atoms. Atoms of the same element are the same. Atoms of the different elements are different. So atoms of the same element are the same. Different element are different somehow, some way. He eventually came up with the idea that it's mass different. And atoms combine in set ratios to form compounds. In set ratios to form compounds. Form compounds. From that, he came up with the law of multiple proportions. That means if you have a set of elements that make multiple different compounds, so you have one set of elements that make multiple compounds, multiple combinations, multiple things. They will form in set ratios. The elements change in set ratios. For example, if you have H2O and H2O2, this is a 1:8 ratio by mass. This is a 1:16 ratio by mass. You double that. If you have a different compound somehow, if there's an HO compound or something like that, you would have a different ratio. So it'd be like a 1:4 ratio or a 1:24 ratio. So the ratios of the oxygens change in whole number ratios. And this led up to the modern atomic theory. Or this came from modern atomic theory. A major problem early on in the modern atomic theory was to find out how many elements, find the number of each type of atom. In a compound. Dalton hypothesized that water occurs HO, because that's the simplest whole number ratio, and then hydrogen peroxide, since it has twice as many oxygens, would be HO2. So they had issues with how many atoms are in each compound. Again, Dalton assumed that the simplest ratio, 1:1, always occurred, in which this case it obviously doesn't. A couple of scientists came up with help on this. Gay-Lussac he studied the volumes of gases before and after of gases reacting to form a compound. For instance, if you burn hydrogen and oxygen, you get 2 volumes of hydrogen for 1 volume of oxygen. And from that, a guy named Avogadro came up with the idea that if you have equal volumes of gases under the same conditions, then you'll have equal number of particles. So if you have equal volumes of gases under identical conditions, you will have equal number of particles in those gases. Which for him, and using Guy-Lussac's results, he said that water would be H2O because there's 2 particles, because there's 2 volumes of hydrogen. This worked pretty good, except for diatomic gases. The diatomic gases really kind of gum things up. If you had like a monatomic atom combined with a diatomic gas, they assumed that oxygen was O, not O2. So this took a while to figure out, come up with the correct solution on this. Parts of the atom. J.J. Thomson. There are several ways that people have spelled his name. Thomson, I think, is the one that's accepted nowadays. He studied cathode rays, and he bent these rays in a tube with electrical force. So if you have a beam of these rays coming through, they pass through a magnetic field or electrical field, and they bent. Then they landed on a screen, and you can tell how much the curvature was. And he found that the bending of this depends upon the weight of these rays and the charge on these rays, which he didn't know either, but he could find out the slope. And that slope gives you the charge to mass ratio, and that was a negative 1.76 times 10 to the 8th coulombs per gram. Many metals, he changed different metals here as a source, and it did not matter what metal he used, he got the same ratio. So he put in lead, silver, gold, iron, copper, and it still did the same ratio. So these particles have something maybe that made him curious. He thought that these are parts of the atoms, but they're not, because they're all the same. So he had to investigate further. So he needed to find out what the mass or the charge was, and that was left to Millikan. Millikan did an oil drop experiment where he zapped drops of oil with radiation, giving them a charge, and he hovered them between a positive and negative plate. He could calculate the charge, he calculated the distance, and the force of gravity he knew. So he calculated the force of gravity with the force of electricity, and he balanced them out, and he found out that the charge of one of these was very, very, very small in fact. And when he put it into this equation up here and solved for m, came out with 9.11 times 10 to the negative 31 kilograms, which is kind of interesting because that is 2,000 times smaller than the lightest atom. Well, if according to Dalton, atoms are the smallest things possible, Millikan and J.J. Thomson just found out something that was smaller than the smallest atom. So therefore, the atom must not be one smallest part, but two different things. The curve went towards the positive, so he knew that these was a negative. And if he reversed the machine, he got a positive thing that bent, and he found out that mass was very, very small. Or, sorry, that curve was very, very small, which means it had a very, very big mass, assuming they had the same charge. And those he called protons, and these negative things he called electrons. So an electron is approximately 1/2000 of the size of a hydrogen atom. The proton is 1,999 out of 2,000 of hydrogen atoms. So therefore, add the two together, you get one proton and one electron, and one proton makes one hydrogen atom. His model that he used was the pudding model, where he had most of the matter being the dough with tiny negatives charges, most of the thing being the pudding, and the small negative charges are that. So this is the proton, which is like the pudding, and the plums suspended in there are like the electrons. Well, people don't know what plum pudding looks like anymore, so I call it a chocolate chip cookie, where the dough is the proton, positive charge, and electron is negative charge. Each one's the same charge. The last bit for this lesson is radioactivity. The infamous story where a guy put a rock on a photographic plate and it developed. When he developed the plate, he found out that it's the same shape and size as the rock. The rock had some uranium in it. So the guy called Becquerel, he discovered this radioactivity. There are three types of radioactivity: alpha particles, which have a 2+ charge and 2 AMU, or the size of a helium atom, or nucleus, 4+ charge. What it is, what an alpha particle is a helium without any electrons on it. So it's the nucleus of a helium atom. Definitely a particle. You got beta, which has a -1 charge, and it is the size of an electron. And what beta particles are just high-speed electrons. They're moving so fast, they're kind of turning wave-like, so you got that wave-particle dichotomy going on there. And the last type of charge is a gamma. Gamma has no charge and no mass. This is definitely not a particle, but a electromagnetic radiation, like light. This ends this lesson on the early atomic models and background. With Rutherford, what he did was he had a shooting gallery, is what I call it. He had some alpha particles, radiation source, uranium, and he shot it at a very thin gold piece, gold foil. And these alpha particles theoretically should have gone, if it was the quantum pudding model of the atom should have shot straight through. 99.99999% should go through. There might be one or two deflections. So he was curious on these deflections, maybe how he can see how the particles of the atoms are packed. Well, he did find that 99.99% did go through, but every once in a while one would ricochet at some crazier angle. And even once in a while they'd ricochet and come almost right straight back at him. He said this is kind of like shooting a machine gun at a tissue paper and then having it come straight back and hit me in the face, the bullet. So something is amiss with the quantum pudding model. Since these are positively charged particles, most of the thing would go through, and only the things that would repel a positive particle would be another positive particle. So he said that the protons were packed into a very small mass, which is 0.001% of the entire atom, surrounded by electrons orbiting like planets. So this is the solar system model of the atom, where the nucleus contained protons, neutrons were not discovered yet, electrons orbited throughout.